Thanks, Mary. So let's start. Thank you, everyone, for joining us for the first HPSC High Performance Statistical Computing Community Presentation Series. Today we will have David Keys. I will leave this to Mary to introduce David. But I just want to, because this is our first presentation, I want just to explain to everyone here what exactly we are, why we did this community, what's the target out of it, and also our next session for the upcoming few months. So I think you can see my screen, right?
Yes.
Okay, so actually we thought about building this community because of 6 different points that we need to post in both the statistics community and also in the high performance computing community. The first thing is to try to bridge the gap between statistics and HPC, or statistician and computational scientist, where they can help each other to do something new through this kind of collaboration. Second is to empowering scalable and accurate statistical method. We have statistical method, we have a robust theoretical method, which actually also coupled with the softwares that can run on laptops and small machines. How we can scale this, how we can go further using HPC. This is the second point of our objectives for this community. Third is having this kind of collaboration as the core, where the statistician can meet the computational scientist and actually what can they do together. And if we can have the first three points, of course, we will be able to build the software tools. We can have an ecosystem that actually manage to run on supercomputer using HPC technologies. Then we will not stop on this. We need a new generation which actually can have the expertise on both HPC and statistics. And this is, we also looking for some presentation talking about the roadmap for training and also for helping young students and young scientists to build their expertise on both statistics and HPC. Then, of course, we are driving this to see the next wave of statistical science or statistical computing in general. So because of this, we prepared some links and also we have one events confirmed at GSM 2026 invited paper session about high performance statistical computing. We have an official website. We have a LinkedIn group. If you are using LinkedIn social media, you can join us there. And also we have a mailing list where you can go to the website and just add your email there, so you will receive anything related to HPSC. And also we are looking for your contribution to the community. So today we'll have David Keys. I will leave this to my colleague Mary Silvana to introduce him. But we have confirmed 3 sessions after David, starting from January going to Feb and March. We'll start first by Ying Song, the professor of statistics at King Abdullah University of Science and Technology. And of course, if you will join our mailing list, you will receive some kind of confirmation about this event. We have the second talk will be from Lisa Radik. She is a postdoc also at KAUST, and she will talk about different category of spatial temporal modeling related to Bayesian modeling. And we will have Dorrit Hamling in March. She is an associate professor of applied mathematics and statistics, Colorado School of Mines. So these are the 3 confirmed sessions. We will try to have a session every month. Maybe we will avoid breaks, but also we are looking for the community to help here, maybe to send us an email if you think that you have something interesting that you need to share with the community. Thank you so much, and I will leave the floor to David.
No, I will do it next. So hi, everyone. Thank you again for joining us. I'm Mary Salvana. I'm assistant professor in the Department of Statistics at University of Connecticut. I am also a co-organizer of this HPSC seminar series. It is my pleasure to introduce today's speaker, Professor David Keys. David Keyes is a professor of applied mathematics, computer science, and mechanical engineering at KAUST, where he was a founding dean in 2009 and founding director of the Extreme Computing Research Center. He earned a BSc from Princeton, a PhD from Harvard, and before KAUST, taught at Yale, Old Dominion, and Columbia Universities. He has received ACM's IEEE Sidney Fernbach Award, SIAM's Distinguished Service Award. He is a Fellow of SIAM, AMS, and AAAS, and was named a Legend of HPC by HPC Wire in the inaugural class of 2024. He has helped bring 4 globally top 20 supercomputers to KAUST and has led KAUST to 4 Gordon Bell Prize finalist nominations. 25 years apart, in 1999 and just recently in 2024, his teams were awarded a Gordon Bell Prize, representing a high watermark of performance on a practical application, one in physics-based simulation and one in statistical emulation. Indeed, we could not have asked for a more distinguished speaker to kick off this HPSC seminar series. Please join me in welcoming Professor David Keyes.
Oh, thank you, Mary. I hope I can be heard and my screen shared. You certainly could invite more distinguished people, but I'm very happy to be the first to sort of set a theme for this wonderful community that you and Same and Mark and others are creating. I've given a title, Statistics, a Spacious Home for HPC, which I'd like to explore for the next 50 minutes or so. But first, I want to tell a story. And first, I guess, before that, say happy Thanksgiving to our US audience. I'm honored if you're tuning in live as an alternative to Macy's parade. And I'm equally honored if you catch the lecture later. Video and slides will be provided at the HPSC website. Amidst statisticians, I feel a bit like a guest introducing his hosts to their own party. I am not a credentialed statistician. My lack of proper statistics education may cause me to overlook some ripe connections between statistics and high-performance computing in favor of connections that I can better articulate. But more than 2 decades ago, I was the chair of a department of mathematics and statistics. I particularly enjoyed my statistical colleagues, in whose interest it was that I should better understand their field and its impact. One of them told me that there are 3 kinds of statisticians. There are theoretical statisticians and applied statisticians, but best of all, there are theoretical applied statisticians. They research statistics as motivated by an impactful application, such as health outcomes, but they seek generalization and understanding rather than concentrating on particular cases of helping medical researchers make sense of their typically noisy data, with its plethora of confounders. However, this helpful colleague never mentioned computational statistics. I'm getting a note that I'm not sharing yet. I thought I was sharing screen 1. It's not coming through. Is it? Do you see the screen, Mary? Do you see the title slide?
I see the presenter's view, so can you make it just the view, just the slide?
Okay. All right. Let's see. Maybe swap displays. Is that better?
Yes,
okay.
Now it's full screen. Thank you.
Okay, good. Thank you very much for that feedback. But this helpful colleague never mentioned computational statistics. There was typically not a lot of data in those days, so an interactive package running on a personal computer was often the only software hardware environment worthy of the data at hand. How that has changed 25 years later. I just referred to feeling like a guest at a statistical party when we talk about HPSC. Now let me switch roles and attempt to be the host for statistical guests at a high-performance computing party. This is a more natural role for me. I hope that it is not merely an adequate one for this talk, but also an interesting and practical one. In the context of big data, classical statisticians are thrown, willingly or unwillingly, into the arms of HPC. So are practitioners of machine learning, which, at least in its regression form, can be regarded as a branch of statistics. The arms of HPC should indeed be wide open because statistics addresses incredibly important challenges, and HPC may be instrumental in helping address them with byproducts of what has been developed for HPC's traditional use in modeling and simulation. Some of the things that HPC can offer to statisticians are algorithms in linear algebra, both dense and sparse, both direct and iterative. And besides being customized to structure in the data, the software for such algorithms has been customized to a variety of architectures. As I like to tell my students, do linear algebra and see the world. One of the exotic worlds in which to immerse oneself is spatial statistics, where, due to massive scale observations, covariance matrices reign. Another realm worthy of immersion is general Bayesian statistics, where precision matrices reign. And to underline my point, the 2024 Gordon Bell Prize in climate modeling was awarded to a team doing spatial statistics emulation, and the 2025 Gordon Bell Prize was awarded to, just last week, to a team doing Bayesian statistics predictions. Hence my title, Statistics, a Spacious Home for HPC. And many other applications await their own HPC re-implementation, often to accommodate bigger data, and many other elements of the HPC ecosystem, hardware, software, and algorithms await greater fulfillment in statistics apps, often reusing existing solutions. So here is the team from Texas and Livermore and San Diego Earthquake Center, along with the Bell Prize and awards chairs just last week on the stage at SC25. And here is our team from KAUST, NCAR, other institutions, including representatives from NVIDIA. That was the November 2024 presentation for the Climate Modeling Prize. So there are the papers. They're available at the ACM online library. Digital twins for tsunami early warning applied to Cascadia subduction zones, and boosting Earth system model outputs and saving petabytes in their storage, two different aspects of large-scale statistical HPC. So this is a picture of Gordon himself. He passed away recently after setting up his prize 38 years ago, and recently, just before passing away, directed a track of it to modeling our climate. Our motivation for starting this community is that data is no longer small, and I don't know anyone who said it better than Dorrit, or earlier, more articulately than Dorrit Hammerling, when she was at NCAR in 2019. Increasing amounts of data are being produced by remote sensing instruments and numerical models, while techniques to handle millions of observations have historically lagged behind. Computational implementations that work with irregularly spaced observations are still rare. If you think about it, a million by million dense, symmetric, positive, definite, double precision matrix requires about 4 terabytes. It's 1 trillion elements. By symmetry, it's half of that, and it's 8 bytes per element. It would take 10 to the 18th flops with a traditional Gauss elimination algorithm, and you know how big a terabyte is and how long it takes to write it. And traditional approaches, therefore, pretended that there was global low rank, which we know there isn't. It's a non-singular system, or they neglected or zeroed out outer diagonals. Better approaches from HPC apply hierarchical low rank blockwise off the diagonal and use reduced precision outer diagonals. The second motivation is that just as data is no longer small, energy is no longer small. And so we have this theme of computational efficiency through tuned approximation, where our objective is to solve with the lowest possible energy, integral of power over time, not necessarily the highest flops rate, but to satisfy application-worthy accuracy, squeezing out easy flops rather than racking them up. But in 2024, performance caught up with efficiency, as thus defined, because 2 trends crossed. We found applications where an increasing percentage of work actually tolerates low precision, And architecture was giving us much faster performance in low precision than in traditional double, especially on the new Hopper chips that year at Alps in Switzerland, starring FP8 and INT8 for some genomics applications. Now, our journey, which was driven really largely by statistics, covers 4 Gordon Bell Prizes papers, in these last 3 years, one on spatial statistics, one on seismic processing, one on genomic association, and one on climate emulation. And I'll focus on the 2 statistical ones in the near slides, where the methods that we applied were Cholesky on the covariance matrix using tile-low rank, mixed precision, and a dynamic runtime system. And both Cholesky and the spherical harmonic transform on a global climate emulation using, again, mixed precision and a dynamic runtime system. And the merits presented to the Gordon Bell Committee were time to solution in 2022 before those lines had crossed, and then both time to solution and a exaflops rate on ALPS by 2024. So our HPC metaphor is that algorithms follow architecture, not because architecture is pleasant for us, but because we don't drive the commodity anymore. AI does. And Wayne Gretzky, many years ago, for those of you in the northeast of the US, hockey fans, a good player plays to where the puck is, while a great player skates to where the puck is going to be, architecturally speaking. And since moving to Saudi Arabia, I converted my sports interest to falconry. So we have, I fly not to where the prey is, but to where it will be. And we now know that falcons actually do calculus, and they can estimate where the prey is and fly directly, not just tangent lines to their current line of sight. Our journey in this tuned approximation world began in 2018 with these time traces for a tile-low rank Cholesky factorization of a dense 54K covariance matrix on 4 32-core nodes of our then Cray XC40, an all Intel Haswell machine. And you can see vertically 128 cores, and time goes horizontally. And this was the standard dense double factorization. And when we applied tile-low rank to the off-diagonal blocks that tolerated very, very low ranks, the runtime reduced by a factor of 10. It scored a lower percentage of peak after squeezing out all those flops that were unnecessary for the accuracy required. It had a poorer load balance, and hence a higher percentage of idle time shown in red. And it scaled less efficiently from 1 to 128 cores. However, despite those demerits from a traditional HPC point of view, it was 10 times superior in running time and about 65 times average power compared to dense, so 15 times superior in overall energy. So this highlights an algorithmic philosophy that we have, that ambitious applications, which are increasingly dynamic and unstructured, mapped onto austere architectures, which are increasingly optimized for uniformity, like tensor cores, require very adaptive algorithms, and this is a full employment program for algorithm developers. Our path towards computational efficiency took, as already alluded to, 2 different swim lanes, one in which we, either by brute force or by adaptivity, low ranked a large number of the off-diagonal blocks, or whereby we, either by brute force, formulaic, or by adaptive means, went to low precision on a large fraction of those off-diagonal blocks, all while conserving our intended double precision accuracy. And this led to a data structure of multiple types of blocks, which had to be, with operator overloading, inserted into a conventional block tile Gauss elimination or Cholesky elimination algorithm. The message was, don't oversolve, maintain just enough accuracy for the application purpose, and economize on storage, no extra copies of the original matrix. So we're now using 4 precisions: double, single, half, and quarter precision in various parts of the calculation. The linear algebraic secret sauce is, where possible, without losing working accuracy, replace double with lower precisions to save storage, save data motion, and exploit special purpose hardware optimized for those low precision tensor cores, and replace default full rank blocks of both the discrete linear operators, the matrices themselves, and also the discrete field data with lower rank blocks, because the data is traditionally smooth, in many cases, just as the Green's function is of the linear operator or of the covariance matrix or whatever, where you have decay with distance. This allows you to compress homomorphically, block by block, without decompression, when a low rank operator operates on a low rank field, also saving storage, saving data motion, and also exploiting these special purpose BLAS3 type operations. The low rank blocks are still BLAS3. They still have some thickness to them. So this leads to a renaissance in numerical linear algebra, where formally dense matrices arising from covariances, Hessians in PDE constrained optimization, in the reduced sequential quadratic programming formulation, integral equations with smooth Green's functions, Schur complements arising when PDEs are eliminated in a Gauss framework, non-local operators born dense from fractional differential equations, those have very low rank, radial basis functions from unstructured meshing, kernel matrices from genome-wide association studies and machine learning. These often have exploitable low rank structure in most of their off-diagonal blocks, if well ordered. For 1D, it's trivial. For higher dimensions, you have to fit a space-filling curve so that things that are near each other in space are near each other in index when they are put into a one-dimensional ordering in memory. And so you have this low-rank structure predominantly off-diagonal. Then many matrices arising in applications have blocks of relatively small norm. They're not only smooth, but they're small. And they can be replaced with reduced precision, which is a 60-year-old tradition, going back to the great Wilkinson, who did his n-cubed factorization in single precision, his residual evaluation in double precision, and did a couple of passes of the low precision version of the matrix in iterative correction to solve to double precision accuracy. A practice which has been taken to extremes in the schools of the late Nick Hyam and Theo Mary, or the current EU whiz in the Horizon project for her in-exascale multi-year software project, Erin Carson, who's now using 5 precisions in getting double precision accuracy and saving a lot of memory and saving a lot of memory motion, which is where the energy goes. So these ideas can be combined, as in this million by million dense symmetric covariance matrix, which stored symmetrically in its original double would be 4 terabytes, but its equivalent replacement for the accuracy required was less than 1 terabyte. So smaller working sets mean larger problems fit in low memory GPUs or fast last level caches on CPUs. For movement savings, there's also a computational savings, which is actually less important given the computational dominance of today's GPUs. But the data structures and programs are more complex. They require you to flatten trees and find batches of blocks with similar rank and precision that can be processed within the same warp. So the rank is a tuning knob where you can go high accuracy to build solvers or low accuracy for preconditioners. You can, and this is very important, you can adapt to hardware parameters like warp sizes or cache sizes by making the blocks appropriately sized or picking the maximum ranks and then reducing the blocks to that rank. And these complement the mathematical structure with architectural tuning. And we can select from a broad and ever broadening algorithmic menu from today's linear algebraic practitioners to cheaply form such low rank blocks and then implement them with skill on accelerators in batches of leaf blocks typically. The options for forming low-rank blocks go beyond the traditional SVD, which is cubic in the block size and too expensive, especially for the repeated compressions that come after additive tile manipulations in an elimination algorithm. But the randomized SVD by Halko and al. Replaces a power of n with the log of the effective rank, very good savings. There were earlier known methods like adaptive cross approximation, which gets rid of 2 powers of n, but it doesn't have the same tuning accuracy guarantees as randomized SVD. And there are even more drastic methods, which are in some sense nice data adaptations. You can subselect a set of columns that you think are dominant and a set of rows that you think are dominant, and then find a matrix U of small dimension that mediates between those columns and rows to form the CUR factored approximation of a matrix A by minimizing the Frobenius norm of the difference, also known as sketching or interpolatory decomposition. In terms of precision, we have a second tuning knob along with rank, and one can consider, for example, the 2-level case of high and low precision and replace a matrix A by a matrix A script shown in the last line showing there, where the difference between the two is less than the high precision on the Frobenius norm of the original A. And this is done by replacing blocks in a script by their low precision equivalents whenever the magnitude of that block in the Frobenius norm falls below the precision ratio. And this can be applied recursively from double to single to half to quarter and so forth. And tiles can be converted dynamically at runtime. So an example from our star of the show, geospatial statistics, where climate and weather applications have many measurements located regularly or irregularly in a region, and prediction is needed at other locations. And these can typically be modeled as Gaussian or Matern random fields with parameters to be optimized to the data, which leads to evaluating inside an optimization loop this log likelihood function, a scalar function of a small vector of fit parameters theta, where z is the large vector of observations and sigma is the covariance matrix constructed according to the chosen form of the model. And in the process of optimizing theta, the covariance matrix must be formed and factored a number of times, and its inverse can be applied and its determinant realized from a Cholesky factorization. So our colleagues have formulated this in a convenient piece of open source software called ExoGeoStat. Here's the C++ version. And it has 3 parts: a synthetic data set generator for testing algorithms, a max likelihood estimator with different optimization methods, using these secret sauces from today's linear algebra, and a predictor or a kriging or a Schur complementation feature that allows the model to be evaluated at missing locations. And some of the kernels that we found handy are shown here with different numbers of parameters in their spatio or spatiotemporal formulas. So ExoGeoStat builds a directed acyclic graph of the Cholesky factorization. You can see here the green nodes represent diagonal block factorizations, and then the reds are propagated down for elimination, and the gems propagated across and so forth. And that's an example of a directed acyclic graph that maximizes concurrency rather than waiting for just the column version of the diagonal traversing version of the algorithm. And it also shortens the critical path to the minimum needed, which is updating each of the diagonal blocks and then factoring it, as you can see in the red, blue, green, red, blue, green, red, blue, green. There's nothing that can be done that shortens it from that, but a lot of the off-diagonal work can be parallelized. And this has been ported to many processor families including various accelerators and many of the top 500 systems as shown on this diagram. So let's apply this exogeostat to a 2D random field or a 3D random field, and looking at the classical n-cubed algorithm on 3 generations of Intel hardware on the top, or the tile low rank version using the StarPU dynamic runtime system. On the bottom, the order n-cubed and n-squared scalings showing as straight lines on this log-log plot with different slopes. And you can see you can either wait for Intel following the red lines, or you can use a better algorithm on the same hardware following the green arrows, or of course have a portable system that maps to the increasingly hostile and austere architectures. That was the operation count side. On the memory side, it's even more dramatic. The savings of tile low rank is shown by these synthetic or real statistical examples. Notice the x-axis is the accuracy threshold. As you demand a tighter fit to the original double precision version, you pay more in memory, but typically you can save an order of magnitude or less and still be, creating a substitute at the 10 to the minus 12th scale. That was shared memory. Here's distributed memory on a Cray XC40, going from 16 to 256 nodes in color, or sticking with just 16 nodes and choosing a better algorithm for the black triangles, again, getting a couple of orders of magnitude instead of 16 times more processors. So there's 2 motivations for mixed precision. It's better than the no precision needed if you have to just drop small blocks. It has a faster time to solution, and it rides multiple generations of NVIDIA very well. Shown here are Volta, Ampere, Hopper, and Blackwell, released in these successive years. And now we know NVIDIA is on an annual release rate for the coming Rubin and Feynman. But you see here the dramatic improvements in hardware going from double to half precision. And if we then expand this, well, first of all, let's observe that between Hopper and Blackwell, double decreased in performance. They invested less in that expensive on-chip real estate in order to invest more in the lower precisions. And they added still lower precisions, going down to FP4 tensor cores, probably not very useful in linear algebra, but of course, okay for the neural network training. And now you see factors of hundreds in scoping out just small factors of bit ratios. And on 512 nodes of Shaheen 3, a CPU-based method system, we, for instance, in factoring a Matern-based 3.25 million covariance matrix in dense or mixed precision dense or mixed precision tile low rank, you can see a savings of about 4-fold in energy to solution, about 3-fold in time to solution. And if you graph those 4 NVIDIA hardware solutions over the different precisions, you see that the savings within a single generation can be a couple of hundred. Over a multi-generation period, it can be 3 orders of magnitude. One more chart of this nature. This time it's in performance, so up is good. And this is 3 generations of Intel just playing with mixed precision where adaptively available. Let's turn to these Gordon Bell thumbnails here. A Gordon Bell paper is very formulaic. It has a performance attributes block, which for us in 2022 on a spatial statistics application, we were going after time to solution because we were getting rid of all those flops, not flops per second. And we were able to run it on a quarter of the world's then #1 system, the Fugaku Fujitsu A64FX ARM system in Riken. This was our team, a bunch of the dynamic runtime system experts from Jack Dorngara's lab at Oak Ridge, and the statistics and computing experts, including several of my dear colleagues here at KAUST. And this is an illustration of the comparison of In blue, the most optimal algorithm, in brown, the dense FP64, and in the intermediate magenta, mixed precision, but still dense. And you see three matrices, strong, medium, and weakly coupled, going from bottom to top, and three parameters, variance, range, and smoothness. So there are 27 experiments here, and you can see that the blue algorithm does pretty well for hitting the exact parameters. In fact, the brown algorithm was often cut off prematurely just because it was too expensive to run it, and it took too much memory. But these are the, of course, traditional box and whisker interpretations. And in terms of mean square prediction error for the Krieged values, all of these methods at greatly different cost and memory requirements basically gave the same results. You could have 3 times less time for the same size problem, 3 times greater size if you're willing to wait the same amount of time on various configurations of Fugaku. I have to add here that these are not optimized numbers. We didn't have much time on the machine, and the dynamic runtime graph hogs a lot of the memory on this small memory per node machine, a problem that is mediated on today's much larger nodes, but has to be taken into account as an algorithm caveat for the modern asynchronous version. By 2024, as I mentioned earlier, the curves had crossed, and so we got both scalability and peak performance, and ran at that time privileged on 4 of the world's top 10 systems, the outgoing and incoming at Oak Ridge, Summit to Frontier, there is. But the best performance was on Alps because they had the new Grace Hopper superchip and they could take us down to FP8. And this was a multidisciplinary team, including Alison Baker from NCAR as our, and Gerastechnikov as our climate whizzes, many statisticians and other HPC people. The motivation was to demonstrate the superiority at the Krieging end for Earth system models, for climate emulators over Earth system models. Earth system models based on PDEs do not perform very well on today's flop-intensive hardware. They're bandwidth limited, but they are extensively used in the climate change community. And the latest instance of that, CMIP6, created more than 28 petabytes, 45 institutions, using the standard PDE based as sort of the gold standard, resolving at quite fine scales, but not making it very easy to do statistical ensembles because of the expense of each individual run, whereby a climate emulator can be trained on a relatively small number of Earth system models with a statistical model in mind to reproduce the statistics without massive ensemble averaging. And their models can actually be reduced to run on small compute resources while still picking up fine scales that had not previously been attained, either in terms of time or space. So this was developed for 54 million spatial locations and hourly resolution over a 35-year period. I won't go into the details of the paper, but just indicate with eyeball norms the strong resemblance of emulations to the actual data that was used to train them, and getting it down to half precision for most of the blocks was no accuracy penalty. The HPC aspects of this in the parameterization above and the emulation below were the spherical harmonic transform, the Cholesky decomposition, and the inverse SHT. The idea here was to take some real climates or PDE simulated climates, subtract out their means, do the statistics on their perturbations, and map them to a regular longitude-latitude grid, which also had the beneficial feature of eliminating some high frequency noise in addition to giving a very efficient means of interpolation. We again used the directed acyclic graph type approach to those large Cholesky formulations, getting heretofore unresolvable fine scales down to 3 1/8 of a kilometer in both the fully latitude-longitude variational form and in a latitude-only form that was often previously used. And again, having the privilege of running on 4 of the world's top 10 systems, which was, by the way, the swan song for Summit. This was, I think, the last computation ever run on Summit before it was retired. Now, happily switching gears to our 2025 Bayesian friends from Texas, Livermore, and San Diego, they won the Gordon Bell Prize with, again, scalability and time to solution, and results measured on a full-scale system. In this case, because they had Livermore colleagues, they could run on the world's new #1, El Capitan, which is normally off limits to those of us in non-DOE secured environments. And their goal was to predict the tidal run-up of tsunamis on various critical West Coast cities like Vancouver, Victoria, Seattle, and Portland, when the big one happens, the big one being the Cascadian subsidence, which happens every 250 to 500 years and has been quiet for 300 years. And during that time, the coastline has been significantly built up with valuable infrastructure and hundreds of millions of people. And they predicted, using a forward model that took enormous expense to compute, they built a digital twin that could predict from sensors that could be detected at at the time of subsidence of the sea floor. So in real time, they could generate predictions of where the tidal run-ups would go. So you can get evacuations going and position first responders. And these are 4 locations on top, 4 locations on the bottom. The prediction with the 95% confidence intervals showing versus the actual realization of the PDE models, and they're really right on top. And it would actually take the waves about 7 minutes to get from the fault to the coastline, but only a 1/5 of a second to predict where those disastrous pileups would be. So this was a nice HPC trick. They separated 3 offline stages, which ran for 250,000 of GPU node hours to generate high resolution models and to train the digital twin, so that phase 4 could run in less than a second. And they scaled extremely well on the expensive pre-training aspects. You can see weak scaling, which should be horizontal on the left, and strong scaling, which should hit those log slope 1 lines on the right. So very high efficiency. So that's basically the demonstration of HPSC that I wanted to make as the main part of this opening lecture. Some success stories from various parties that we expect will inspire and enable a real plethora of success stories in stretching the data availability of models today. But what I would like to do to finish up is to just basically show a movie. I mean, I'm not going to tell the full stories, but I would like to sort of put on display, for statisticians in particular, but maybe HPC people will like to nod along with it, some universals in HPC algorithms and software. These are things that you wouldn't do in just a proof of concept app to get to your final answer, but you must do at scale. And also talk about 12 elements of the HPC ecosystem so that HPSC can just ride the HPC wave. They don't have to reinvent all this stuff. And in so doing, they will greatly enrich the existing HPC ecosystem with new impactful applications and probably stretching the techniques into new algorithmic creativity as well. So what are these 12 universals? I'll read them quickly. Reside as high as you can on the memory hierarchy. Reduce synchrony of distributed memory codes in frequency or in the span. Reduce communication in the number and or the volume of messages. Employ dynamic runtime scheduling and balancing to go beyond bulk synchronous processing. Avoid over-resolving with respect to output accuracy requirements. Reformulate applications before computing. They don't always come to you in the best way to map onto the architectures available. Exploit your constitutional right to reorder, getting the same answer with different loops and partitions and subroutine boundaries and so forth. Exploit multiple hierarchical versions of the same system, doing most of the work on the small version, getting the answer on the fine version. Exploit data sparsity to meet the well-known curse of dimensionality, whether it's polynomial or exponential, with the blessing of low rank, using physics or causality. Take resilience into algorithm space and thereby relieve a lot of the expense and time of doing all resilience in hardware and in operating systems. Code to specialized backends to provide a nice narrow waist API to users from a variety of apps to a variety of ARCs. And consider multiple parallel programming models within the same application. So for each of these, I have a one-slide HPC demonstration that I can't really talk through, but you're well acquainted, presumably, with the cost of going further down on the memory hierarchy. Registers are 1 cycle away. A disk is 10 million cycles away. DRAM is embarrassingly 100 to 1,000 cycles away. But more importantly, going to DRAM or sending a message across a network costs you hundreds of times more energy than doing a double precision flop, like a floating point multiply add. So that's the motivation for residing in high-level cache and in blocking your computation so that you have good temporal locality there. In terms of reducing synchrony, oftentimes you can use free flops to save global reductions. Like in conjugate gradients, instead of conjugating every vector, you could store up a bunch of unconjugated vectors and then do some dense flops and synchronize much less. And here's an example on the bottom right of a speed up of 2.5 coming from just grouping some orthogonalizations or some conjugations rather than doing them every time. You can also get rid of communication with extra memory if you happen to have extra memory that's fast access. And Jim Demel's group at Berkeley has gone through all of direct linear algebra, LU, Cholesky, QR, Gram-Schmidt, eigensolvers, showing how there's a actual theoretical lower bound on the amount of communication needed if you have extra memory on given nodes. And many algorithms actually attain these theoretical lower bounds. Our KAUST colleague, Dalal Sukhari, has taken eigensolvers to town with respect to these directed acyclic graphs, bursting through traditional subroutine boundaries and through traditional loop orderings to squeeze out a lot of idle time shown in white on the top right to get a more efficient, energy efficient solution on the bottom right. What do I mean by not over-resolving an output? Depends on what your output needs. If you only need the heat flux in this convection cell of maybe cooling some semiconductors with a fan, then the mesh on the right can give you as accurate an integral of the normal derivative of the temperature as the mesh in the middle. The mesh in the middle is needed to get, like, say, single precision accuracy everywhere in the domain. But depending on your output of interest, you can use that surrogate on the right. And you can use such low dimensional surrogates many times, even if you wanted the solution everywhere to high accuracy, if it was part of a optimization loop, in the early iterations. This is fundamental work out of MIT from 25 years ago, from the applications perspective. Of course, many times the person who gives you a problem gives it to you in a basis or in a formulation that is suboptimal for your architecture, and it's your job to do a transform to some other space where it can be solved more efficiently and put back. Sometimes it's hard to do that inversion, but this is always something you should think about. As Vladimir Rokhlin of Yale always taught me, think, full stop, then discretize. Choose your basis elements appropriate. You should exploit the right to reorder. This is a CFD calculation that we did 25 years ago for another Gordon Bell Prize, showing a factor of 5 in 2 different formulations, one 5 unknowns per point, one 4 unknowns per point, by simply interlacing fields versus their default vector, doing some structural blocking to replace a lot of unstructured integer operations with 1 integer per block instead of 1 integer per entry, and edge reordering to improve cache temporal locality, reuse something as soon as it was just recently used when calculating all the conservation law residuals. And you can see the dramatic improvements from default per time step. Whenever you can, exploit multiple hierarchical versions of a problem. Here's the problem of finding the forces on every target particle from every source particle. And a fast multipole method reduces that n-squared computation to order n by making local expansions, aggregating those expansions, translating the aggregates, re-expanding them locally, and only the particles that are in the same cell and the immediate neighboring cells have to be handled directly with the n-squared algorithm. I've already alluded to a 2023 Gordon Bell finalist that was in the frequency domain for seismic processing. And here you see a roofline plot showing that the implementation on this high memory bandwidth Cerebras architecture actually hit its computational peak, whereas all the other conventional processors on the bottom it's still in the memory bandwidth bound range. Take resilience into algorithm space. A lot of times we can tolerate errors in a iterative method where residuals are recomputed and liquidated. And here's an example from Sandia where they purposely injected floating point faults to show that some versions of GMRes would still adequately converge. Code to specialized backends. This is just the hourglass model. Many apps, many architectures, a good interface. Use multiple parallel programming paradigms. You may have a very efficient, let's say, divide and conquer paradigm, and you may be able to have a very blessed, map reduce version where a whole bunch of sub portions of your machine are doing this tightly coupled thing, but they're doing them independently until the very end where they vote. So you can find out more on these HPC universals from a 2021 article in the Communications of the ACM, where they noted our successful student placement in the DOE labs from a very unlikely Arabic concentrated source. And we had a chance to describe this program. So I don't have much time left, but I'm just going to breeze through 12 elements of the HPC ecosystem. In fact, I'm not even going to breeze through them here. I'm just going to show the movies. So, we have a culture of validation, verification, and uncertainty quantification. Validation, are we solving the right equations? Verification, are we solving the equations right? Uncertainty quantifications, do we have a ball of certainty around the answer? Repeatability, replicability, reproducibility. Can you repeat your own calculation? Can an independent group repeat it using your tools? Can an independent group reproduce it using tools developed independently? You get a badge of ACM if you have that. Tool standards like MPI, which made message passing universal across all vendors in all languages at great expense and great negotiating skill from the chaotic days of early parallel computing in the 1980s, when if you wanted to move from one machine to another, you had to recode all your messages. We have roadmaps in HPC, so you can predict and proportion memory and bandwidths and latencies and everything for future generations of supercomputers. These have been remarkable at following, Moore's law down to the nanometer range. And this is all inherited if you join the HPC caravan. I referred to benchmark problems like the M6 wing from Onora. Every CFD code gets tested against these. Do we have these standard problems in spatial statistics and Bayesian statistics. I'm not sure that we do. We're starting to get them in machine learning, of course, but this is a goal. We have benchmarks that track over time the trends in architecture, whether it's dense or sparse linear algebra, bandwidth limited iterative linear algebra, AI, concentrated tensor core, and so forth. We need those, and you can ride them. We have virtuous cycles of data to models, of questions to computations, to hypotheses, insights to technologies, to archives. All of this is, something that is automatically inherited. We have verticals in all of these areas: oil, gas, pharma, agriculture, and so forth. And a lot of the bottom lines of these verticals are re-amortized. We have human-computer interactions for intuition in complex models. We have the validation verification loop and the performance loop to create computational instruments that can be used efficiently by non-expert users. And then we have this hourglass reproducibility. We have the convergence of paradigms where each of simulation, analytics, and learning augment the other by, for example, providing training data, or by providing physics-based regularization, or replacing models with learned functions, steering in high-dimensional spaces. Traditional simulation doesn't learn, but if you open the box and you have this interaction between analytics learning and traditional simulation, you get a better tool. Such campaigns like HPSC benefit from motivational manifestos presented to funding agents, presented to deans creating curricula, and so forth. And I'm happy to announce that just today, by coincidence, a paper co-authored by many of your sponsors in this enterprise appeared in the Wiley Interdisciplinary Reviews for Computational Statistics. HPSC Challenges, Opportunities, Future Directions. For my money, the best thing about this paper is 300 references that really help, drill back into the origins of some of these important things. But I commend my colleagues for this nice laying out of the field, like this graphic, which shows how HPSC rides the HPC wave in architectures, frameworks, and different applications. I would conclude by saying, here at KAUST, and hopefully where you are, we're interested in sustainable supercomputing. That means computing energy efficiently and computing to support the UN Sustainable Development Goals, like clean energy, agriculture improvement, climate modeling, and so forth. Here's the motto: do linear algebra, see the world, from the World War II recruiting poster for the Navy. Here is some follow-up, and I turn the session back at the top of the hour to my hosts.
Thank you so much, David, for that insightful talk on how HPC and statistics can work together. So now we're opening the floor to questions from the audience. Are there any questions? I guess I can start.
Okay.
How was your experience working with statisticians? Because you're coming from the computer science side, and we also have many papers. I'm coming from the statistics side. So, yeah, what's your experience?
I think you planted this question, Mary, because I often tell my statistics colleagues that they are the best reason I came to KAUST. I mean, when I came, by the way, when we started KAUST, we didn't really have many practicing statisticians. We had the Texas A&M advisory people from our global collaborative research, who quickly corrected that. Stanford, which was hiring our applied math faculty, actually didn't hire any statisticians for us, but we corrected that through largely the persuasive offices of Marc Gintal. And it was really the statisticians who were eager, who saw that we were making good use of Shaheen, and who said to themselves, hey, that's an advantage. Shaheen, by the way, is the name of our series of top 20 supercomputers from 2009 until this year. And that's the way that our collaboration began. And it's been really an educational, a very pleasant side-by-side, elbow-to-elbow educational thing. We've trained a lot of students together, and the uptake in both directions has been very gratifying. Of course, I love my engineering colleagues and so forth too, but I've learned more and thought more because of the stresses that statistics put on HPC.
Thank you so much.
Thank
Any
you.
questions?
No, I don't have. I'm sorry.
Hi, Jan.
Yeah, hi, David.
Maybe I'll ask a question then. Can you
Thank
hear
you,
me?
Mark.
I can
Yes.
hear you, Mark.
Yes, okay. So thanks again, David, for a very stimulating talk. I enjoyed this your presentation. I was thinking about the statisticians who are attending the presentation are interested in learning more about HPC. Now we have some resources for them. There is the review paper on HPSC. There's the HPSC for Science website with a mailing list, as mentioned by Same at the beginning of the session. Do you have some other suggestion for statistician who want to learn more about HPC? What do you think they should do?
Well, one thing that's sort of inspiring and where their presence would be very welcome is to attend one of the regular HPC meetings, the Supercomputing Conference in the US, if you can get a visa these days, or International Supercomputing Conference in Germany every June. And those are the conferences where the large systems of the world are re-ranked on a 6-month basis. And they draw, people who are very interested in performance and energy efficiency. And I was very delighted this year that there are, I think, 4 sessions, each of which contained 4 selected tech papers on sparse matrix methods, sparse direct matrix. That was something that, Gauss would have done, but we're still doing it because the architectures keep making it more interesting to try to get performance out. And, this is driven largely by, precision matrix analysis from the statistical side. But, the selectivity of this conference is very high for presenting, like it was 22% out of 600 tech papers this time around. But the other part, which is totally in parallel, is the exhibitor forum on the floor, in the big convention center. So there's these 2 parts going on, and then there are the vendor meetings. So it's a great way to get plugged into the HPC community and see what people are working on, where people are doing, especially the open source work, where people have applications that because you're a statistician, they're not, using statistics correctly yet or at all. And so that would be a way of getting wide exposure in both directions in a short time. But in terms of journals from the HPC side, there's the International Journal of High Performance Computing Applications. There is the SIAM Journal of what used to be called Scientific and Statistical Computing, but now it's Scientific Computing. And that of course has a plethora of algorithmic oriented papers that are related to scalable computing. But I think the best thing they could do is get in touch with people on this new community. We've had some really good, let's say, predecessors like George Osterhoff before he left Oak Ridge in retirement, who was always pushing this direction. There are many others out there, and join the interface. There's more problems at interfaces than in the domains on either side.
Okay, thank you.
Thank you.
There's a question from Richard Smith.
Okay.
Okay, thank you. Richard Smith, University of North Carolina. Thank you, David. That was a very interesting talk.
Thank you for joining.
A previous question I was asking you about your experiences of working with statisticians. Could I ask you what are your experiences of working with climate modelers? Are they using these sort of techniques in their modeling experiments?
I would say the majority of climate modeling projects that one hears about, in particular the ones funded by NSF and through NCAR, through Department of Energy, and various European. They're predominantly working on the PDE-based models, which are poorly mapped onto today's high-performance computing system in terms of memory bandwidth limitations. Now, there's another generation of climate models coming along, which use neural networks like the Pangu climate model in China, which is able to have incredibly accurate predictions, that go along with the PDE-based conservation models, but at the price, of course, of trillions of parameters. So whenever I, hear people talking about machine learning of climates or weather, I like to say, hey, do you believe in Gaussian processes? You don't need a trillion parameters. You may need, a non-stationary model with, a few parameters in each domain. So I think that statistics is underused compared to the easy default of building neural network models today, in many cases that could be done with regression. Now, of course, there are classification problems, recommendation systems. There, the neural networks are, the method of choice. But many times they're being used and accurately and profitably for regression problems, where a thoughtful dialogue with statisticians could probably greatly reduce both the training and the inference. That's my humble opinion.
Thank you.
Thank you.
There is a question from the chat. From your perspective, what is the most significant near-term application for hybrid quantum classical computing in an HPC environment like KAUST?
Okay. First of all quantum computing is going to be hybrid quantum classical for a while, because we need the memory of the supercomputer to store the quantum state. I think the nearest term successes are not going to be what is paying the bills in quantum computing these days, which is crypto and decryption in particular, but rather material science and quantum chemistry. That is what Feynman said in 1982. We haven't gotten there yet in terms of the the reliability of quantum hardware, of qubits, but the natural systems to evolve with quantum computers are quantum systems. They have there's time-dependent Schrodinger equation, which can be put into a quantum circuit. The other class, which is ripe for exploiting, is quadratic unconstrained binary optimization problems, QUBO. Fortunately, it starts with a Q. And those map well onto analog quantum devices like D-Wave, simulated annealing. There's good optimization work to be done, practically coming soon there, and good materials simulation work. The latter requires, I believe, a classical supercomputer. Every time you add a qubit, you double the memory that you need to emulate it. So, I think Shaheen 3 could probably emulate 50, quantum bits at whatever price it was, $100 million. If we want to go to 51 quantum bits, we need another $100 million, right? So that's the phenomenon of, in some sense, quantum efficiency, exponentially speaking. But right now, I think there are several examples internationally of a hybrid quantum noisy system next to a supercomputer. The best paper at ISC 2025 was on just such a system at Munich in the LRZ. And it's a hot area. NVIDIA has just announced NVQ-Link, not NVLink, which we've had for years, very efficient message passing. NVQ-Link, which provides both a standard interface to about 23 quantum vendors, plus FP4, 4 petaflops of FP4 AI to do quantum error correction, which will greatly accelerate the use of quantum hardware. I'm not recommending buying any particular quantum device yet. I'm interested just in developing quantum algorithms, but I think that NVQ-Link will greatly accelerate the creation of hybrid quantum classical. I don't know whether that's going to have much relevance to statistical emulation yet. That's for other experts on this call to figure out. But it's a great question. It's one that is constantly being revised in these annual conferences. There's now a quantum village at supercomputing. 24 vendors trying to engage.
I don't think there are any more questions. Thank you so much, David. Okay.
Thank you for the invitation and for launching what will be a very interesting website, and for lead authoring the manifesto that we need.
Yes, I hope everybody reads that paper.
Yep.
So if there are no more questions, then we will send announcements to our mailing list. So please don't forget to subscribe. And thank you so much. Have a nice day.
Happy
Bye-bye.
Thanksgiving.
Yes.